to the two parts will be the forward and inverse kinematics, because this is a fundamental mathematical modeling of the robots. And today we'll be covering the differential kinematics, which is a Jacobian. So we have already seen this diagram for many times. So this is a serial manipulator. So here we have the robot frame, which is the base frame. And here we have the end-effector frame. So for forward kinematics is that we already know all the joint values and how can we calculate the end-effector frame. So we have all the motors values and what is the position of the end-effector. So that is the forward kinematics. And for the inverse is we already know our pose of the frame. So we already know which aiming position we want to go. So what's supposed to be the joint values of the robots. So inverse over the reverse is the inverse kinematics. So we have joint positions, and if we have the joint positions, then through the forward kinematics, we can know the end-effector's position. And if we already have the end-effector configuration, like we know what is the position and the orientation of the end-effector, through the inverse kinematics, we can find out what is the joint values. So what is the robot Jacobian? So the relations between the motion is the velocity, the joint space, and the motion in the task space, which is in the Cartesian space. So we have already know that if we have a forward kinematics and we put in all the theta values, and what we can get is the X, or you can say is the joint. And here is the end-effector. So from this way, it's the forward kinematics, and the reverse is the inverse kinematics. And what is the differential kinematics? Is that we want to have the theta dot, and we want to find the velocities of the robots. So it is the instantaneous velocity mapping can be obtained through the time derivation of the forward kinematics, or in the geometric way. So there are two types of Jacobians. So basically, we are using is the analytical Jacobian, but we also introduce the geometric Jacobians. So the analytical and Jacobian is just you will be obtained by time different variations, and the geometric Jacobian is through mapping the joint rate to the twist. So this was just for introductions. As we already know that for the angular velocity of a rigid body, the v, which is the velocity here, is equal to the angular velocity times cross your vector. So if we have a point, this is the angular velocity is omega, and this is r. The velocity over here of this point is equal to omega cross r. So this is the velocity. So this is from the, I think the dynamics. I think you all have already learned during your undergrad. So for the geometric Jacobian, the end-effector instantaneous velocity can be represented as this. So this is the Jacobian metric for the linear and Jacobian metric for the angular And this is the Q dot means that it's the joint rate. And equal here is the linear velocity of the n effector and the angular velocity of the n effector. So here we just give you the introduction for the geometric Jacobian. So if we have the joint, this is joint I, the I joint. So this is a reverse joint. So the linear, we can refer back to here. If we have a link, this is a link. And the omega means the joint velocity. So here we have the V is equal to your Z I minus 1. This is the omega cross your P I minus 1 to E. So this is your R. So it's Z I minus 1 and times beta dot I is the omega. So this is the omega. And cross, and this P I minus 1 to E. So I minus 1 is here, and the E is the n vector. So P I minus 1 to E is the R, is the displacement. So here is the R. So together, we can find the velocity of the n effector. So this is how we formulate the velocity of this point. And again, if we see the rotation, the direction, so the direction will be same as your theta, the omega here. So for omega is equal to your Z I minus 1 times theta I. So this is how you formulate the rotation joint, the reverse joint. This is called the prismatic. And for the prismatic joint, if we see a prismatic joint, so this prismatic joint can move, the velocity is like this one. So what is the velocity here? Should be same as this point, right? Because the velocity here is moving. And this is a rigid body. So the velocity at this point is same as this joint. So if you see like, this is a prismatic joint, it means that it's moved linear. And the velocity, so the velocity of this point is same as here, the joint. So the velocity will be the same. And for directions, because we know that the prismatic joint doesn't change the directions. So for the prismatic joint, the velocity is same as your joint velocity. And for the angular, the direction is 0. So this is how you map the geometric Jacobian. And we can see an example. So I think you're very familiar with this 2R arm. So the first link is the A1, and second link is A2, and it's connected by 2 joints, which is the first joint, the Q1 joint, and the Q2 joint. So we know that the Z which means the joint axis, so it's here. So x is equal to 0, y is equal to 0, and z is equal to 1. So the joint axis is like this one. And the p, the position of p O to E, this is here to here. So we already solve, this is the for kinematics. And for the P1 to E is like this one. So it's A2 times Q1 plus Q2. So if you are still not familiar with the for kinematic, we can do it again. So this is the point O, and this is point E. And this is A1 and A2. So the position of the E for the X is equal to A1 times cosine Q1 and plus A2 times cosine Q1 plus Q2. Because you can know here is Q1. And for the Y is the sine. And for Z is equal to 0 because it's a planar robot. So for Z axis is 0. And if you want to find this one is the 1, so 1 to E. So from this one, we know that for this vector is equal to A2 times cosine Q1 plus Q2, and A2 times sine Q1 plus Q2, and then 0. For this vector. So these two are all relative joints. So we can refer back to our equation for the relative joints for the geometric Jacobian. We know that for the linear velocity should be zi minus 1 cross pi to I1. So we can have this one. And for the angular Jacobian, should be Z0. And we can just cross it, and we can get, this is the geometric Jacobians. All these two are. So what is this metric stand for? So you know that for the A1 cosine Q1 minus A2 cosine Q1 plus Q2 and minus A2 sine Q1 plus Q2. I think the first one should be, maybe it should be sine. I'll check it afterwards. And it's 0, 0, 0, 1. And for the second column is also 0, 0, 0. So this is the geometric Jacobian. So what we want to times afterwards is time Q1 dots and Q2 dots. So the Q1 dots means the angular velocity of the first joint. And the Q2 dots means the angular velocity of the second joint. And what we can get, if we times these two matrices together, what we can get is the x dot, y dot, and z dot, and also the three rotations. So if we times the Q1 dot and Q2 dot, and we times these two matrices together, we can get the velocity of the nth vector at the x, and also the velocity of the nth vector at in the direction of y. So that will be all for the geometric Jacobian. So it's just for a brief introduction. So what will be mainly focused is on the analytical Jacobian. So this is the derivative. So I hope you still remember how to do the derivative from your calculus class. But here is very simple, very simple derivatives. So these are the like partial derivatives. I think we will come back later after we introduce the analytical Jacobians. So the differential kinematics is the relationship between the joint velocity and the corresponding nth vector linear and angular velocity. And this is mapped, so the mapping is described by a Jacobian matrix. So here you can see this is the Jacobian matrix, and which depends on the manipulator configurations. So what you will do is basically, if you still remember your forward kinematics, so this is your forward kinematics. And here is your joint. Maybe this line. So for 3R, we have 3 joints. And through the forward kinematics, or maybe we can get just doing the examples for 2 arms. So it's the same. So if you can still remember from your forward kinematics, the value of your joint 1 and value of joint 2, and you times your forward kinematics, and you will get your x and your y and your theta, the position. So is this one okay? If you still remember what is your forward kinematics, it's okay. So this is what you have done in the forward kinematics. So here we have the Q1 and Q2, and here this one is the matrix, and we get here is the Px, Py, and theta. So for this robot, the forward kinematics is the L1 sine So this will be for fluid kinematics. So we input is the Q. So again for the fluid kinematics. So it will be equal. It's L1 cosine Q1 plus L2 cosine Q1 plus Q2. And here is L1 sine Q1 plus L2 sine Q1 plus Q2. And here is Q1 plus Q2. So this is your fluid kinematics, and this is your any effective position. So let's go back to the differential. So we know that we need to derive it by times. So we know that zero dots, for the dots means that it's derivative by times. So we just derive by times. And here we get is the x, the velocity in the x direction, and the velocity in the y direction, and also the angular velocity. And here, because that we know that we want to derive it by t, so we need to do the partial derivatives. So it is L1 cosine Q1, so divided by Q1 times Q1 divided by t. So this is the partial derivatives. So here is L1 sine Q1 and divided by Q2. So here is Q2 divided by t. And Q1 so here will be so we finished the first one, and for the second one it's the same. So this is how we do the derivative for the Jacobian matrix. So for this one, this is the position. So this is velocity of the any factor, and here is the position and divided by partially divided by q, and we have the q dots. So this one is the q divided by the time. So if you do the q dots, this means the angular velocity. And here will be the Jacobian matrix. And for the orientation, it's the same. So this is the angular velocity of the any factor, and this is the any factor poles, and divided by q, and we have the q dots, which is the q divided by t. And here this is the angular Jacobian. So in total, we can formulate our analytical Jacobian through the time derivatives. And we'll show you how to work with so this is the same. So we have these two formulas. So Px equal to A1 times cosine Q1 plus A2 times cosine Q1 plus Q2. So this is our fluid kinematics. We know that this is P. So directly we can derive by times. So if we are not doing it in the matrix form, we can get so for Px is equal to A1, or you can call it L1 because just now we used the L1 plus Q1 plus A2 times cosine Q1 plus Q2. And we just do the time derivatives. So we derive by time and also derive by time. So here we can get is px dot, which means the velocity in the x direction. And here, q1, and we'll do the partial derivatives, is q1 and times q1 and t. And for the second one is W for the second term is cosine q1 plus q2. So derivative by q1 plus q2. And here with q1 plus q2 and divided by t. So we know that for cosine, we can get in minus sign. So it's minus a1 times sine q1. And here is q1 dot. And for this one, it's minus a2 times sine q1 plus q2. And times this one is q1 dot plus q2 dot. So for the x, this is for the x position, and we derive by time, and we can get the velocity in the x direction. And this is our, which we solve it by time derivatives. And in the y directions, it is like this one. So we can write it in the matrix form. So we would like to write these three equations in the matrix form. It's like px dot, py dot, and theta dot. And in the middle is the Jacobian. And here is q1 dot and q2 dot. So what is this Jacobian like? So we know that this one is a minus a1 times sine q1. So it's minus a1 times sine q1. And this times q1 dot. And here is minus a2 times sine q. q1 plus q2. So this one times q1 gives you this type. And the second one times q1 gives you the first half of the second term. And we have another one is times q2. So here is a1, a2 sine q1 plus q2. And for the y is the same. So it's a1 cosine q1 and plus a1 cosine q1 plus q2. So it's a2. And for the second column is a2 cosine q1 plus q2. And we see here is q1 dot plus q2 dot. This means that it's 1 and 1. So if we multiply, it's q1 dot plus q2 dot. So this will be your Jacobian matrix. So it maps the angular velocity of the motors for the joints to the n effector position, the velocity of the n effector. So to sum up, we can just use the partial derivatives. If this one is usually derivative by q1, q2, and q3, And also, for the second terms, we can just derive by Q1, Q2, and Q3. And for the angular, it's also Q1, Q2, Q3. So this is your full kinematics. And you just do the partial derivatives. And you can get your Jacobian. So if you see this one is your full kinematics, so you just do your partial derivatives. The px derivative by q1, and px divided by q2, and px divided by q3. And also for second row is py and divided by q1, q2, and q3 respectively, and for the theta also. And together you can get your Jacobian matrix. So this is how you derive it by the px divided by q1. So for 3R arm, we know that px is equal to a1 cosine q1 plus a2 times cosine q1 plus q2 plus a3 times cosine q1 plus q2 plus q3. So if we see the first one, we want to derive this one by q1. So we can directly do this one. So it's equal to a1 times minus sine q1. And for the second one, we can use the partial derivatives. So if you see it's a2 cosine q1 plus q2 and divided by q1. So we can use partial derivative q1 plus q2, and here is q1 plus q2 and divided by q1. So the first one is equal to minus sine q1 plus q2, and the second one times, because we know this is q1, and for the q2 is to q1 is just a constant, so it's 1. And same as the terms, so we can get is the 3 terms. And for the px divided by q2, because if you see from q2, q1 is a constant, so you can just, if you derivative a1 cosine q1 by q2 will become 0. Because this is q1, the variable is q1, and it is divided by q2, so it will become 0. So you just apply the partial derivative to the equation, and you can get these 3 solutions. And also the py is the same, and for theta, because this one, the theta is, or the phi is the q1 plus q2 plus q3, so it's all 1. So to sum up, you just fill in your solution to this matrix, and you can get your Jacobian. So here is q1 dots, q2 dots, q3 dots, and times this Jacobian matrix, and we will get the velocity of any vector in x, y, and theta. So this is the time derivative of the Jacobian matrix, to get the Jacobian matrix. And this just gives you a reference to how to get the time derivative of a rotation matrix. But you can just refer to it if you are interested, because this is just to solve the screw matrix and to show how to do the time derivative for the rotation matrix. It's not really a method. So for rotation matrix, if you do time derivative, then you can get the Q times your axis. And why we do the Jacobian matrix? For one of the purpose is that we want to do a mobility analysis, because we know that for robots they will have many singularity points. So for the mobility analysis, if we use Jacobian, we can find out the singularity configuration of the robots. So if a Jacobian matrix has a max rank in the configuration Q, that means that the robot's n vector can move in any direction of the task space. So like normally, like just now we have the planar robots. So it's Px, Py, and theta. So we have the three degree of freedoms. It means that it can move in x direction and y direction and the rotation. So if we have a Jacobian, it's full ranks. That means if we multiply the two matrices together, all these three have values. But once it's like the rank is less than the maximum, it means that you may have like something 0, 0, 0 here. So if you have this one, you Q1 times 0 gives you 0. So all this one, you cannot find what is your angular velocity. So if you have 0 over here, this means that you cannot find your velocity in y direction. So in this case, this is not full rank. So in mathematical point of view, why it says that if the Jacobian has max rank in the configuration Q, that means that the n vector can move in any direction of the task space. So this is the direction of the task space. So if this has the full rank, that means that all here have values. So you can just times this matrix with your joint angular velocity, then you can get your velocity in any directions. So if rank Jacobian, rank of the Jacobian matrix is less than your max rank, that means that there is at least one direction of the n vector cannot move. So it's instantaneous. That means it's cannot move at this configuration. So configurations where the Jacobian loses rank, so it loses the instantaneous mobility of the robot's n vectors. This means that there is one direction in the task space you cannot move. So if you lose the rank of in your y directions, it means that in this configuration, your robot is not able to move in y directions if you lose your rank. So that means it is in the singular configuration, or you can say it's in singularity. So we cannot find a joint velocity that realizes the design effective velocity in the arbitrary direction of the path space. So if you are very close to a singularity point or singular point, a very large joint velocity may be needed to realize some velocity of the effect. So normally, if you modeling a robot or if you design a robot, you'll find out all the singularity configurations, and you'll try to avoid to approach near this point, because if you are near this point, you'll need very large joint velocity to cross the, like, if we have a singularity at this point, so if you move near this point, the more near this point, you'll need a larger instantaneous velocity. So if you touch the point, then sometimes your robot just cannot move, because you may lose your rank if you are at these configurations. And maybe we can just take a break first. Configuration of the robots. So we can avoid to go near this singularity point. So to find these kind of configurations, what we do, because we want to find full ranks, so we can just use the determinants. So if the determinant of the Jacobian matrix is equal to 0, that means that at this configuration, the robot is in the singular configuration or singularity. Because if your determinant is 0, it means that one of your row or column is all 0. So this will give you the determinant is equal to 0. So this is how we check whether the configuration of the robot is in singularity configuration or singular configurations. So finding all singular configurations of a robot with a large number of joints or the actual distance from a singularity is hard to computation task. So if you check a lot of papers of the robotic papers are proposed the method to find the singularity configurations. So if we see 2 are on, so just now we have derived this Jacobian matrix. So if we want to find a singular configuration of this robot, we can just use determinant this equal to 0. So we can just basically use the determinant, JQ is equal to 0. And we can find, so it will give you A1 times A2 times sine Q2 equal to 0. And A1 and A2 are the length length, so sine Q2 is equal to 0, then you will have singular configurations. So we know that for sine Q2 is equal to 0, Q2 will be equal to either 0 or pi. So if Q2 equal to 0 or pi, then these robots will be in singular configuration. So if you see it in the geometric, Q2 is equal to 0 means that it's stretched in a line. For pi, it's folded. So the singular configuration will occur in these two circumstances. And also the singular configuration corresponds here to the Cartesian point on the boundary of the workspace. And in many cases, these singularities separate the regions in the joint space with distinct inverse kinematics. So it's like the elbow up or down. So if we see between the elbow up and elbow down, the middle will be going straight. So separate the two different solutions for your inverse kinematics. For elbow down and elbow up, so in the middle will be a singularity configuration. And we try to find a singularity for a polar arm. So for kinematics of this polar robot, is Px equal to Q3. Q3 is this one, times cosine Q2 times cosine Q1. And for the y is here, and z is d1 plus Q3 times sine Q2. So like for d1 is here, and sine Q2 is this one. So the z value is d1 plus sine Q2. And we know that for here is Q3 times cosine CR2 means here, and cosine Q1 means here. So it's cosine, if you type Q3 times cosine Q2 comes to here, and times cosine Q1. So this is the value. So you can get your Px, Py, Pz. And we formulate it into a Jacobian matrix. It's like this. You just use the partial derivative to do with the so it's Px and partial derivative by Q1 and Px partial derivative Q2 and Px Q3 and Py. Here is theta. Okay, so we have Pz over here. This one. So this will be our Jacobian matrix, and here will be the Q1 dot, Q2 dot, and Q3 dot. On the left side is your Px dot, Py dot, and Pz dot. It's the velocity of the any vector in x, y, and z direction. So we can see the Jacobian is like this, and we can see the determinant is Q2 squared times cosine Q2. So it's the same. So for cosine Q2 equal to 0, we'll get the plus and minus 90 degree. So for simple singularity, it means that the rank, if we have the rank of the this Jacobian is normally will be 3. If we drop to 2, will be a simple singularity. And if we have dropped to 1, it means that Q3 equal to 0. So if you see Q3 equal to 0, so always 2 column will be 0, so the rank will drop into 1. So all the singular configuration corresponding here to consistent point internal it to the workspace. And I think we have introduced the inverse schematic last week. So for last week, we introduced the analytical inverse schematics. Here we will introduce another, is the numerical inverse schematics. So normally if you go into industrial, all the industrial robots use the numerical method. So this is the basic or the fundamental, the basic formation for the differential inverse kinematics. So I think if you have done your homework for last week, the inverse kinematic for a 6R robot manipulator is very, very complicated. So in industrial, we usually use the differential inverse kinematic, which is also called the numerical inverse kinematic method. So a highly nonlinear relation between joint space variables and rotation space variable called non-solution or redundant of the closed form solution for inverse kinematics. Or sometimes just the analytical inverse kinematic is too complicated or too hard to find. Then we will use the numerical method. So a linear mapping between the joint velocity space and the operational velocity space in differential kinematic equation tackles the inverse kinematic problems. So this is the differential on the Jacobian method. We know that the velocity of any vector, and this is the angular velocity of the joint. And in between is the Jacobian matrix. And we just remember this relationship. So the desired joint velocity Q dot depends on the desired position and orientation of the any vector. And can be obtained by very simple inversion of the Jacobian matrix. So if we invert it, so we know that the velocity of the any vector is equal to the Jacobian matrix and times the Q dot. So we just invert it, and we times the Q dot over here. So it's the Jacobian inverse times VE equal to inverse times J Q dot. So it will give the inverse Jacobian times VE equal to Q dot. So this is always from the compound. Is the Q dot equal to Jacobian inverse times the velocity of any vector. And to use this method, the Jacobian must be invertible. And the condition that the matrix can be invertible is that the Jacobian needs to be a square matrix, and also the determinant of the matrix should not be 0. And in MATLAB, you can use this function, invert is INV, to provide your matrix inverse. And if you have the matrix is not square, then there's some pseudo inverse can be used, but it's not really recommended. So if we see this formula, so the Q dot is equal to the Jacobian inverse times your velocity, any vector velocity. And if we assume that time, the very small interval of time, t, so we times the times on the both sides. So the Q dot times t, it means that it's the joint velocity times the times. It means the joint displacement. And it's because it is a very small interval, so it's a very small displacement of the joint. And our any vector velocity times t, it means a very, very small displacement of the any vector. So here we map the displacement of the joint and the displacement of the any vector together. So to visualize this, it means that if we have a here this is the joint velocity, and if we times this joint velocity times t, So it means that it's a displacement of the joint. So here it's map a V at the end vector. If we times a very small interval of time, and it gives the displacement of the end vector. So we can use this invert Jacobian to map the joint displacement and displacement of the end vector. So it is something like integration of the time. So if we see this one, the displacement of the joint, and this is the displacement of the end vector. So if we aiming, this is our aiming configuration. We know that the position we want to go is here. So we can just take the difference between the current position and our aiming configuration. And this will be the delta E. Then we can just use the Jacobian, the invert Jacobian here to map the delta E we want to travel to the joint displacement here. So this is how we map the displacement of the end effector and the displacement of the joint. But if you remember that there's a very big mistake over here, it's because that we know that the Jacobian matrix will change in each configuration. So if your configuration is different, then your Jacobian matrix will not be same. It's unlike your inverse kinematics or forward kinematics. Inverse kinetics and forward kinematics is all the same, no matter what configuration of your robot is. They will have the same modeling. But for Jacobian is you have the Jacobian of matrix in each configuration. So your Jacobian matrix will change when your global configuration changes. So we map this end effector displacement at a joint displacement at using the Jacobian of this configuration, the current configuration. So there should be some errors. So this is the change in actuator space. This means change in your data. And for the delta RE, it means change of the end effector. And in between is your Jacobian inverse. So it is the current actuator space. So therefore the joint space after the adjustments should be something plus the current. So this is the Jacobian inverse. And we can see this is using the analytical inverse. But because this one is very simple, so the Jacobian inverse is, differential inverse is almost the same. But if you see in the graph, the output using the analytical inverse will be just a very straight line. And using the Jacobian inverse, you'll have some noise in between them. And this is the differential inverse kinematics. So you can see the error scale is around 10 to the -3. But the analytical inverse is 10 to the -15. So it is almost have no errors at all. And differential inverse there has very small errors. So it depends on your iteration, how many. So if you are moving, the smaller the steps, the time, the smaller time, so it means the smaller the displacement, your precision will be higher. And differential inverse results has error, so the error compensation method could be applied. So this is a loop for if you are using the numerical method. This is our desired position, and this is our current position. So you'll find the difference or the errors, or you can say it is the distance between your current and the desired position, and you'll find this, the error, and you use the Jacobian inverse, and you use your Q dot, and to use the Q dot, then you can find your Q, what is the displacement of the joint you need to move, and then you send back to your forward kinematics, and you calculate the new current position, and using the same loop. So hopefully, like in few iterations, then you can come very close to your targets. So the E is equal to your desire minus your current, and we want it to become 0. Because become 0 means that your current configuration is match your desired configuration. And these are some error compensation method. So in summary, the analytical inverse kinematics, the advantage is absolute n-effector pulse and absolute joint space conversion, and theoretically there is no errors. So if you have errors, is your calculations, they don't have so many digits to recall the memory, and the disadvantage is very difficult to derive the formula, and they may have multiple solutions. So the analytical inverse kinematics is which we covered last week. And this week we covered the Jacobian inverse kinematics, or you can call it a numerical method. So the advantage is you have a systematic way to derive from the forward kinematic equations. Since that for serial robots, the forward kinematics is very easy. If you using the DH method, you can derive your forward kinematics equations. Then you can get your Jacobian. And it's ways to automatically handle multiple solutions, because the Jacobian, the inverse kinematics, or the Jacobian inverse kinematics, or you can call it numerical, you will always generate one solution each time. And for disadvantages is increment of the n-effector pulse. So you need your current configuration and also your current joint configurations. And there will be errors due to approximations, but through iterations, if you set up a threshold, the errors can be very, very tiny. And this is the normal robot control system. So it's the desired configuration, you will send it into the controller, and the control will send the low power controls to amplifier. Then the amplifier will have a high power control and send it to the actuator and transmissions. And also use derive the force and torques, and also the motion forces. And you use the sensor to check, and back to the controller, check whether your current configuration is same as your desired behavior. So if not, you're still doing the closed loop until you match your desired behaviors. So this is usually in the robot's controller. And because we know that we have the errors, so this is the desired data, and this is our current. So if you minus it, it's the error. And this is how we try to find the steady state of the errors. And For the feed-forward control, this means that we don't use the closed loop. We just our desire, and we send our data. So what we use in the practical, like also motors, is the feed-forward control. We don't have a closed loop. We don't have a sensor to get back. And feedback controls means that we will have the controller can have some sensing data, so we can form a closed loop. So normally we will have a feed-forward plus the feedback controls. And these are all for today's. So today the most important is you will know how to derive the analytical forward kinematics. So it's through the partial derivative of the forward kinematics. Sorry, I will say it again. So today is you will find how to derive your Jacobian matrix, and it's partial derivative of your forward kinematics. And then if you invert this Jacobian matrix, you can use this invert matrix to find your inverse kinematics through the differential inverse kinematics solution. And any questions for today's topics? So I think this will be the last one, a lot of mathematics. Then afterwards will be applications. Yeah. So basically, for the fundamental mathematical modeling of the robots is the forward kinematics and inverse kinematics, and then the Jacobian. It's only so if you can manage to know these three methods, then I think all the modeling of the robots then you can do it. So we will also have a group exercise today. So actually will be same as last week. So last week you will derive your analytical here should be it's correct. So the first thing is that you will derive your analytical Jacobian of the robot model. So it is the same model. So the first problem is you will find the forward kinematics and do the partial derivative of the forward kinematics. Then you can get the analytical Jacobian. And then the problem 2 is use the differential inverse kinematics approach to solve the inverse kinematics. Same as last week. So last week, you need to find your analytical inverse kinematic solution first, and you can solve it. And for this week, you'll use the numerical method. So this one should be problem 3. For mistake. So problem 3 is compare and discuss your solutions, because last week we were using the analytical inverse, and this week we're using the numerical inverse. So you will compare and discuss the difference between these two solutions. And this is for your group for the practical exercise today. And if you have not finished last week practical worksheets, we still bring our 3 degree of freedom robots here. You can still continue to do. And for homework today, it's very easy. You just derive the analytical Jacobian and also formulate the geometric Jacobian of the farmer robots. So this is just time derivative of your forward kinematics. Wait a minute. The forward kinematics is very long. Or maybe we can just cancel this one. Yeah. Okay, so maybe we just formulate a. Okay, never mind. We don't have homework today. Okay, so we will just only have the in-class exercise. Okay, so if you have any question, you can come on and ask. Yeah, no more.
So we can forget about the homework.
For today.
Just for today.
Yeah.
We have to do it, but not today.
No.
But we still need to upload it.
Yeah, we don't need to upload.
Okay, so good afternoon everyone. Today we still have a in-course critical, right? So in the second problem, you need to use the numerical method to solve the inverse kinematic. So we have prepared a script, a MATLAB script. You can find it on Moodle, and we've cut off some critical block so that you can input yourself. But let's see the whole process about this script. So first, you have to input you guys can look at the MATLAB script in the Moodle so that you can understand what I'm saying. But that's we will watch it together. But so first, still, you need to let the script understand what your robot is. So you need to still input your DH parameters. And then since it's a numerical, so you will have a initial guess. So you have to put in your initial theta. In your script, I believe it's 0, 0, 0. So it's still our 3 degree of freedom robot arm. So 3 theta is required. And then use for kinematic of this theta, and then you can have the position of your robot arm's position in this current. And then you can use this position to calculate with the target position, and then you can derive the position arrow. With this position arrow, then you can drive this script. So first, you need to see if the whole algorithm is converged yet. So you have a convergent check. So right here in the script, you can see the arrow is setting, tolerance is setting to 1e-6. And if it's not convergent yet, then you need to use Jacobian to find the theta dot, to find a new theta. So right here, we have this equation, x dot equals j, which is Jacobian matrix theta dot. And by inverse, by left multiply a inverse Jacobian, and you can get a this theta dot. So right here, with this as an I, you can get this equation. So with this equation, you know the new theta dot right here. So you get a new theta dot. You can use it in your integral, and then you can find a new theta k plus 1. So with this new theta k plus 1, you can have another iteration right here. This is an iteration. So you can calculate a new arrow and see if it's convergent yet. So this is the whole concept of this script. Okay. So in this script, we also have a convergence plot to see how its convergence goes, how its arrows go. And then we will plot a final posture to see if it's correct. Okay, so two functions we will use today, we need to discuss a little bit. Is first is cross. In cross function, you need to first you need to give it a two matrix. So we can use this to find our Jacobian. And because our 3 degree of freedom robot only cares about its position, because the posture is all dependent to the position. So we only care about its position. So we only need this one. And then to inverse the Jacobian, we here in our script we use P-inf, which is pseudo inverse. Although Professor said it's not recommended, but in our script P-inf is more stable. So maybe you can try in your personal and try what will happen in inverse, but you have to make some modification. Okay, so that's the structure today, and let's see the script. So here, this one. So just like I said, first we have to input our DH and our initial guess. So right here is 0, 0, 0. And then we give a target position, so we can calculate its arrow between the current position and the target position. And in this iteration, the first thing you have to input is right here, is how you calculate your delta x. Okay? So delta x is where we've been talking about the Jacobian right here. Oh no, the delta x is the difference, sorry. The delta x is the difference between the target and the current position. You need to have a delta x right here first. And then the second block right here, you need to find your theta dot, which is derived by the Jacobian. And then you have to derive the Jacobian with P-inf, so that you can have an inverse Jacobian. And then the third block right here, that is you have to use your integral to find the new theta, so that if it's not converged yet, in next iteration you will have a new theta. Okay? Do we have any problem right here? So this is the only 3 block you have to input. Think carefully and discuss with your teammate how to properly input these 3 blocks, and then I believe that you can make this script wrong, and then so you can finish your problem too. Alright. If you haven't finished the robot exercise last week, you can do it today, and that's it for today. And you can start all your practical. Okay? If you have any problem, just come to me. Okay, thanks.